Hello everyone, I am Sixun Huang from the National Kaohsiung University of Science and Technology, Taiwan. Today, we will introduce the recurrent neural network RNN in its simplest form, which has been widely used for dealing with sequential data. To clearly explain what the RNN is, we use the problem of price forecasting as an example. The outline of this lecture includes introduction about the RNN model, its main concept, and an example of price forecasting using the RNN model. RNN architecture, about the state and the parameters for modeling the RNN, the recurrent steps for inference in the RNN model, and a price forecasting example by the RNN model. RNN training, about the overview of the training process and the definition of loss generally used in the RNN model. What is the RNN model? The RNN model is for dealing with sequential data S1, S2 to Sn consisting of n items. The number of data items could be changed over time, and the data items are mutually dependent. For example, given historical prices, the problem of price forecasting is to predict future prices. In this problem, the data to be processed is sequential and with different lengths. For example, on day 4, we have 4 prices used to predict the price on the next day. But as time goes by 2 days, we have 6 prices for prediction. Obviously, in the price forecasting problem, the prices are dependent on each other. The main concepts of the RNN model for dealing with sequential data are recurrence and using state. Recurrence is to repeatedly perform the same task for every data item. This allows the RNN model to deal with the various length data sequence. For the data item S1, the RNN model firstly processes it and produce the output Y1. For the next one, S2, the RNN model does the same thing and produce the output Y2. The RNN model repeats the same process until the last one. The next concept of the RNN model is to use the state for memorizing past information. This makes the RNN model possibly models the dependency among data items. More specifically, the RNN model keeps a state variable initially as H0. Then the RNN model involves the state over time from H0 to H1, H2, until Hn. To detail the main concepts of the RNN model, we take price forecasting as an example. Assume that we have a historical price sequence consisting of 7 past prices. The objective of price forecasting is to predict the next price in the sequence. Since many machine learning models perform much better on normalized data, the prices are firstly normalized. The general way for normalization is according to this equation. Subtract the mean mu from the price, and then divide the resulting value by the standard deviation sigma. This makes the prices in the sequence with 0 mean and 1.0 standard deviation. In this example, mu and sigma of the prices in this sequence are 85.52 and 0.97 respectively. By applying this equation, we will have the normalized values here. In this price forecasting example, we take 4 values for predicting the next one. Accordingly, the input will be a 4-dimensional vector, and the output is a predicted value. In the first round, the input S1 of the RNN model is these 4 values in green color, and the output Y1 is 0.06. Next, the input S2 will be the next 4 values, and the output is 2.01. Until the input is the last 4 values, the output of the RNN model is the value that we want to predict. After introducing the RNN model and an example, we next detail the architecture of the RNN model and how it works. As mentioned, the model state H in the RNN model is used to memorize past information. Since the model state H cannot be directly observed, it is hidden, and is a H absolute dimensional vector, as shown here. Here, the vector dimension H absolute is a constant and should be specified by the user. The model parameters theta, including W and V, are the weights in the RNN model and are shared across times. W is the input weights, U is the state transition weights, and V is the output weights. Since model parameters W, U, and V are shared across times, the RNN model can be folded as this one. Since the RNN is a recurrent model, the RNN inference can be formulated as follows. Given an input ST and the previous state HT-1, the objective of the RNN inference is to output YT. It consists of update and prediction stages. The update stage uses W and U to involve the state from HT-1 to HT. After that, the prediction stage is to use the state HT to output YT by using V. The first step of the update stage is to transform the input ST to the state UT by W. The transformation from ST to UT can be expressed as this equation, where T denotes the transpose. Since ST is a X absolute dimensional input vector, and UT is a H absolute dimensional state vector, this makes W be a H by X absolute matrix. In step 2, it uses U to involve the state from HT-1 to HT- by this equation. Because both HT-1 and HT- are H absolute dimensional state vectors, U is thus a H by H absolute matrix. In step 3, it fuses the data from the input and the path by directly adding UT and HT-. Finally, it applies the activation function tangent H to compute the state HT. Here is the definition of the tangent H activation function, which maps the input value to the range between 1 and -1. In the prediction stage, it uses V to transfer the resulting HT a H absolute dimensional state vector, to YT a Y absolute dimensional output vector. Accordingly, V mapping from HT to YT is a Y by H absolute matrix. Here, we take price forecasting as an example to further explain the RNN inference. As before, we take 4 values for predicting one value. This makes the dimensions of the input and the output spaces be 4 and 1 respectively. Besides, we model the state as a 2D vector and initiate to a 0 vector. Under such a configuration, W mapping from input to state will be a 2 by 4 matrix. U is for state evolution and is a 2 by 2 matrix. V is to transform the state to output and is a 1 by 2 matrix. Here, let the model parameters W, U, and V be these 3 matrices respectively. The input S1 in this example is this 4-dimensional vector. Then, we detail the steps of the RNN inference in how to obtain the output Y1. In the beginning, we transform the input S1 to the state U1 by multiplying the matrix W as shown in this equation. Thus, we have U1 in the blue rectangle. Then we involve the state from H0 to H1 minus by multiplying U. Since we initialize the state as 0 vector, H1 minus is also a 0 vector. In step 3, we fuse U1 and H1 minus by addition. Finally, we apply tangent H activation function to all values 0.02 minus 1.16. This results in a new state H1 as this vector. In the prediction stage, we transform the H1 to Y1 by multiplying the matrix V as shown in this equation. We obtain the output value Y1 equal to minus 0.98. To obtain the actual price, we can unnormalize Y1 by multiplying sigma and adding mu that are computed before. In this case, the predicted price by the RNN model is 84.56. After introducing RNN inference, we talk about how to train an RNN model. Firstly, we split the data sequences into k data segments S1, S2 to Sk, and then randomly select a data segment Si from S for training. The selected Si is used to flow through the RNN model to produce the output sequence. The loss between the predicted and the ground truth sequences is computed and used for updating the model parameters W, U, and V. Here, we give a figure to detail the training flow more clearly. By giving a data sequence, we split it into k data segments. We randomly select one data segment Si and take it as input to the RNN model. The RNN model will predict an output sequence. Then, the loss between the predicted and the ground truth sequences is computed, and a well-known backpropagation algorithm is used to update W, U, and V. Next, we will talk about two loss functions that are widely used in the RNN model. The loss function is for measuring the error between the prediction sequence Y1 to Yn and the ground truth sequence Y1 head to Yn head. In the RNN model, there are two widely used loss functions: mean square error MSE for value prediction, and cross entropy for classification. These two equations are the definitions of these two laws. Obviously, our example price forecasting is a value prediction problem. It takes MSE as the loss function to train the RNN model for price forecasting. This term is for average, and this term calculates the total square errors of all items. For this selected price sequence Si, taking S1 as input to the RNN model, we'll predict Y1 equal to minus 0.98. The corresponding ground truth Y1 head is the next value in the sequence, that is 0.06. By running RNN model again, we have Y2 equal to 1.95 and Y2 head equal to 2.01. Finally, we have Y3 and Y3 head equal to 1.21 and 1.29 respectively. Accordingly, the MSE between these two sequences can be computed as this equation. Because there are three items in the sequence, the term for average is 1 over 3. The total square error is the sum of these three terms. After simple computation, the MSE loss of this example is 1.09 and is used for updating model parameters W, U, and V. This video introduces the RNN model for dealing with variable length and mutually dependent sequential data. The main concept of the RNN model is to recurrently deal with the items and use a state to memorize the past information. Plus, we give a price forecasting example to explain the RNN model in a step-by-step manner. Thanks for your listening and have a nice day.